variables we'll cover on this Wednesday. Okay. Any questions? I expect you guys to do better in the first test, especially the one who promised me, practically you're going to do better. So I want to quickly recall what we're doing here. So we are still looking at the triple integrals. Okay. So now the integrating function involves three independent variables, x, y, and z, and d is the region in R3. Right? So we discussed several different types of integrated region. And this d is a region in R3. So I want you to quickly recall when we were talking about the graphing, okay? When we were talking about graphing involving triple integrals, what we only graphed is this region in R3, right? We didn't really graph the function. Everything? The only thing we graphed is this region in R3. And I mentioned the graph of a function involving three independent variables is in R4, right? So the only thing we did is actually graphing the region in the integrating integral, okay, right here. And the region we discussed, beginning from the easiest case, the cube, where the region D is equal to x is bounded between two numbers, y is bounded between two numbers, and z is between two numbers as well. So this is really the easiest case. And in this case, we can write down our triple integral in 6 different representations. Now with me? We can write down the triple integral in 6 different representations. Each one of them can be transferred to the other in a very easy form. For instance, if I have my integrating order dy, dz, dy, dx fixed, then the only thing I need to do is to keep up these pairs of numbers with the integrating order right here. All right? So if the interior is with respect to z, so I want to have p, q inside. All right? The middle integral is with respect to y, so I want to have c, d in the middle. Right? And x goes to the outside, so I want to have a, b for the pair of numbers in the outside. So you can write down your integrating order with respect to x, y, z in 6 different orders. Right? So every time you write down one representation, you're supposed to keep up with the pairs of numbers right here. Right? And these things are pretty easy to transfer between the 6 representations. And there are 6 different integrating orders. And I can practice one more. For instance, I fix my integrating order to be dy, dz, dx. What should I have?
C to D.
So x goes outside, so I still have to have a and b in the outside. Z goes to the middle, so it's p and q, and y is c and d. Same integrating. Okay? And this is how you put down for triple integral if the integrating region is Q. You can write it down in either one of the 6 representations. And a way of evaluating a triple integral is exactly the same as the single variable calculus. Right? So when you're looking at the interior integral, you're eliminating the variable z, so y and x are both constants. All right? Are both constants. And then after we eliminate the variable z, which means we already evaluated the middle, the very interior integral, we are not supposed to see any variable z. All right? So we already eliminate the variable z, then you pair off the variable y by regarding x as a constant, and so on. So every step of eliminating one variable is a single variable integral. All right? So this is the way of dealing with the Q. What is more interesting is so-called z simple, y simple, and x simple regions. Okay? So z simple region domain D is x, y is a region in xy plane, and Z is bounded between two functions of x, y. Okay? So I give you two different ways of understanding what this region on the xy plane is. One way to understand it is if you have an intervening region in R3, you can squeeze everything back onto the xy plane. And what the projection is exactly the region R here. And so that's one way to understand where you can get this R. The other way to understand where you can get this region R is this region D is actually built upon this region on xy plane. All right, so you can look at the region D and see where this D is coming from. So basically, these two understandings are equivalent. Either you can squeeze or you can see where this D is built upon. All right? So you need to squeeze everything back down to the xy plane, and this is how you single out the variable Z here. So I single out the variable Z. Z is beginning from G1 of xy, G2 of xy, where my function is f xy z, dz, dx, dy. So if it is z simple, I want to have the z integral in the interior. And then depending on the type of the region R on xy plane, I can represent this double integral involving x to y in either x simple or y simple, right? So I give you this term, so z simple in the space, x or y simple on a plane, right? So if it is a y simple, that means I need two numbers for x and two functions for y. So I need two numbers a to b, and then g1 of x to g2 of x from g1 of xy to g2 of xy f xyz dz dy dx. Here is y simple on the xy plane. Okay, so if it is a z simple region, always single out the z variable first, and then you deal with x, y separately. You just look at this region on xy plane and use all the skills involving double integral. Okay, in double integral we talk about x simple, y simple. We talk about even polar coordinates regions. You use all the double integral skills to identify this part. Okay, irrelevant is the interior. Okay.
Okay, so when you're trying to find out either a y simple or x simple, the dz is always first, right? Okay.
So x simple and y simple on the xy plane, that means I already single out the z variable. It has nothing to do with z variable anymore. I'm just looking at this region on the xy plane and see what it is. Okay? Any other questions? So similarly, we can identify this region as an x simple region as well on the xy plane. In that case, I need two numbers for y, c to p, and from h1 of y, h2 of y, g1 xy, g2 xy, f xy z, dz, dy, dx. So this is x simple on the xy plane.
Shouldn't it be dx, dy?
Oh, sorry, dx, dy. Thank you. Dx, dy. Again, the way of switching the order of dx, dy, and dy, dx has nothing to do with z. Everything has nothing to do with z. You already single out the variable z. You're just concentrating on this part. And this is strictly a double integral. Okay, this is strictly double integral with a region on the xy plane. So it can be regarded as a y simple, or in two numbers for x, and two functions for y, or it is a x simple. Okay? And we also talk about y simple region. So in a y simple region, my region is identified as xz is in R, where z is bounded between g1 of xz and g2 of x. So I should say R here is a region on xy that is why we can identify it as a y simple or x simple. Here, R here is a region on xz plane. Okay. So in this case, as long as I know it's a y simple region, I can always single out one of the three variables in the very beginning. Then I only needed to deal with the other two. All right. So similar strategy as what we did here. So I will single out G1 of xz to G2 of xz, f xy, z, dy, dx, dz. Okay, so I will single out the variable, y variable in the very beginning, and then I'm looking at this region on xz plane. I can identify it as either x simple or z simple. All right, either x simple or z simple. Again, there are two ways to understand how you get this region R. My favorite one is you can squeeze this D as a region in R3 onto the xz plane. Okay, onto the xy plane, you're squeezing the vertical, right? So you're squeezing vertically back in the xy plane. If it is xz plane, you need to squeeze in this direction, in the y direction. Right? You project everything back onto the xz plane and see where this region R is. Now, if I have this region R on the xz plane, I can still identify it as a z simple, where I need two numbers for x and two functions for z. All right. So it is a to b. Let's see. I have g1 of x, g2 of x, g1 xz, g2 xz, f xy, z, dz. So in this case, it is z simple. Okay. So similarly, I can identify it as x simple, which I need two numbers for z and two functions for x. In this case, I have it as an x simple region on the xz plane. Okay, so I need two numbers for z and two functions for x. So this is x equals w1 and x equals w2. Okay? Are with me? So generally, you peel off the first variable, and then you don't need to worry about it. You look at the double integral and concentrate on this double integral, regardless of what is inside. You identify that strictly as a double integral. Okay? So most of the triple integral skills are directly coming from the double integral, as long as you can do the very first step. All the following works are pretty straightforward. And the very last case is so-called x simple region. So in x simple region, my yz variables are coming from a region on yz plane, and x is bounded between two functions of y and z. Okay. So I want to quickly write down the two identifications. If it is x simple in the space, z simple on the yz plane, or x simple in the space and y simple on the yz plane. Right? So essentially what I'm doing here is, if it is a cube, I can write down the 6 representations directly, as long as I keep up the intervals with the variables. If it is in a general case, if I'm switching between the general cases in the 6 representations, it's much more challenging here. I can still do that, but in every transformation, I need to identify all this required information. All right? I can still switch between these 6 different orders, dz, dy, dx, to dz, dx, dy, or to dy, dz, dx, and dy, dx, dz, or the other 2 orders I'm going to write down right here. So if it is x simple, I need a d1 of yz, d2 of yz, f xy, z, dx in the very interior. And then if I want to have dz, d1, which means I'm identifying the double integral involving yz as a z simple region. So I need 2 numbers for y and 2 functions for or I can identify as dx, dy, dz. As long as I give you an integrating order, you should be very smooth about what it means. It means x simple in the space, and if I project onto the yz plane, it is y simple on the yz plane. That's me. As long as I give you one integrating order, you should be able to see what information is required. I need two functions for x involving y and z. And then I need two functions for y involving only z. And for z, I just need two numbers. All right? And if you're doing this over and over again, you're pretty smooth about what it means. For x, you definitely need two functions involving the following two variables. Okay? And for y, you definitely need one and two functions involving the only other variable. Only in this case, you can eliminate all the variables when you peel off the three integrals one by one. All right? Okay, so this is going to be p to q from w1z, 2z from g1. Let me finish this one first. Okay, thank you. F, x, y, z. Yep.
Sorry, I just have a question.
Mhm.
Why did you pick that order? Dx, dy, dz?
I can pick any one of the 6 different orders, right? If you notice that you have 1, 2, 3, 4, 5, 6. So there are 6 different orders. The only thing, or the most important thing, which is different from the cube case, is in the cube case, I can identify either one of the 6 different representations, and then you can write down these intervals directly with no difficulty at all, right? As long as you keep the order, then that will be true. Whereas in the general case, I have to be super careful, all right? In the general case, I have to be super careful. In the case that every time I have an integrating order, I don't have the 6 different numbers anymore, right? I have to keep up with all the required information regarding the functions. I have to put the functions in the correct order, okay? So this is a pretty nice kickstart for you guys to come back from the spring break. So 6 different representations for 3 different variables. And we have discussed the cube case and this